So with example number 9 is slightly different than example number 8 in that in this particular case, we're asked to calculate the pH of a solution in which we have a 25 mils of a 0.1 molar hydrochloric acid solution being added to 30 mils of 0.106 molar sodium hydroxide. So we have to remember that the reaction that we want to write, which is the reaction that we would have written last year, is a neutralization reaction, in which case we have HCl plus NaOH will react to form the H2O and the NaCl. The issue then is that the NaCl really are spectating. They're always aqueous at this point. They don't form a solid. So the things that actually drive this reaction are the formation of the water, which means that H plus OH minus will react to form water is really the reaction in question that we're looking at. Now, the other thing that we have to keep in mind is we have to keep in mind what's going on in terms of changing these things to moles so that we can really have an idea of the actual amount of the things that we're working with. So molarity is equal to moles per liter. So I know that we have 0.100 molar for my HCl. I want to find the number of moles, and I have 0.0250 liters. And when I calculate that all the way through, I get something like 0.00250 moles of HCl. So that'll go down here. For my hydroxide, my sodium hydroxide, again, molarity is equal to moles per liter. So we have a 0.106 molar solution. Moles over, we have 30 liters, or 30 milliliters. And that's going to give me a all right, now, going and talking about in terms of which one is going to be the limiting reactant, which one of these things will appear to run out first? The H plus. So for my water in this particular case, again, we're not going to be all that concerned about it because it's water. But down here, I'm going to have 0 for my H plus, but the number of moles of OH that I'm going to have is 6.8 times 10 to the minus 4 moles. Now, just like yesterday, we can use a little bit of stoichiometry to go ahead and determine the concentration at this point. So for my hydroxide concentration, I'm going to be using moles divided by volume of the solution, which in this case will be the 6.8 times 10 to the minus 4 moles over the volume of the solution. So we had, let's see, it was 0.00, nope, too many zeros, 0.0250 liters plus the 0.030 liters. So when we go to calculate the concentration of the OH in this particular case, we end up with 0.0124 molar OH. Now, we are asked to calculate the pH. So the way that my head decided that I was going to do that was I was going to take the pOH, which will be equal to the negative log of the OH minus. So the pOH will be equal to the negative log of the 0.0124. So the pOH would be equal to 1.91. which my pH value will then be equal to 12.09. Questions about that? In this particular reaction, what will be the major species after the reaction? The OH minus will be my major species. And the pH in this case will be greater than 7. So that's not too bad. Yes, sir.
So can you solve it this way, like every time? Because I know, like in example 6 or whatever, we did this pKa plus log.
Okay, so that's a good question. In example 6, we were working in a buffer system. Okay. And in example 8, we're talking about a titration. And example 9, we're talking about a titration. Okay. Now, we do need to have a brief discussion about titration curves of weak acids and strong bases. So we finished up the strong acid, strong base. Now we need to talk about the weak acid, strong base. So in this case, we have to imagine that we have a weak acid in the in the flask, and we are adding sodium hydroxide to it. Again, note that the equivalence point here, that this curve looks different than the strong acid, strong base. Here is the curve for the strong acid, strong base. Like, that's the generic curve that we're used to looking at. And I want you to note or see that a couple of things. First of all, the starting pH is higher than the strong acid pH. Also, I would like you to note that the equivalence point appears to be greater than 7 here, and that's important. And I would also want to point out, that there is a buffer region at the midpoint, or there's a buffer region, and at the midpoint of the buffer region, pH actually equals pKa. So that would be when your concentrations of your acid are equal to your concentrations of your base. Does that make sense? Okay, so with a weak acid, strong base titration, you have the equivalence point, in which case moles of acid equals moles of base. Okay, and in this case, the moles of acid equaling moles of base will have a pH greater than 7. It won't be neutral. But in the buffer region, you are going to be in a situation where there is a midpoint of the buffer region, in which case the pH will end up equaling the pKa. And what that means is that the concentration of the acid will be equal to the concentration of the base in the buffer. So that's subtly different than what we talked about yesterday. Now, we're going to answer these questions in a second, but before we do, in order to completely neutralize the acid, what volume of sodium hydroxide would be necessary to have been added according to this curve? Yes, you are right. It would be 40 milliliters. Remember, the equivalence point is moles of acid equals moles of base. They're neutralized. With that in mind, what volume of sodium hydroxide would be needed to reach the half equivalence point? Note the half equivalence point is the special point in the middle of the buffer region. So how much would that, or what would be the volume of that? That would be about 20 milliliters. Now, the question is, what is the majority species at the half equivalence point? So yeah, the issue is that the concentration of the acid and the concentration of the base are equal, which is different than the moles of acid, moles of base being equal. So we could probably say that which majority species, we would say that there is none. But what is the majority species before the half equivalence point? It would be the acid. What would be the majority species between the half equivalence point and the equivalence point? The what? So the base. And what is the majority species after the equivalence point for sure? Total base. Okay? So we have to kind of analyze these guys. Does that make sense?
What does PR stand for?
It's just a made up.
Oh, like an hour?
Yeah, I just made something up. Yeah. Can I go forward?
Yeah.
All right. That I want to like talk about this for a second. So before titrating, so we'll come back to that slide. So when you analyze in a weak acid strong base titration, before titration has occurred, there's only the acid present. Once any base has been added, but before the equivalence point, you have both weak acid and conjugate base present, and that will mean that there's a buffer present, so you're gonna have to use a buffer calculation. At the equivalence point, all of the acid is gone, and the solution is all conjugate base, which at that point, the conjugate base will undergo hydrolysis, and you have to calculate a new concentration of the conjugate base because you know that the volume has changed. You have to calculate, you have to use the KB, or calculate the KB rather from the Ka of the buffer region. That is the Ka of the weak acid. And you have to find the H3O plus and solve for the pH when you're at the equivalence point. Once you've passed the equivalence point, you simply can use stoichiometry to determine the number of moles of hydroxide and use the new hydroxide concentration with a new volume, and then you can calculate the new pH. Now, to go back, yeah. Yes. Yes. So in this case, we are now going to be calculating the pH of a solution formed when you have 45 milliliters of sodium hydroxide being added to a weak acid, in this case, the acetic acid. So in this problem, the first thing that we need to kind of identify is what's going on here. So I'm going to write the reaction, and the reaction is we have the CH3COOH reacting with the sodium hydroxide to produce the conjugate base. Well, actually, I'm going to back up here. To produce this and eventually the water. Now, I'm going to rewrite this so that we get rid of the spectator ion, which in this case is the sodium. So okay, now, the next thing that I'm going to do is I'm going to have to determine the number of moles of each of my starting substances based on what I've been given. So in this case, the number of moles of acetic acid, again, molarity is equal to moles per liter. So that's 0.100 molar equals moles over 50 milliliters. Which will give me a value of and for my sodium hydroxide, I'm going to take the and I should get a value of and at this point, there will be none of the acetate ion formed, and we are not going to worry about the water. So now, which one of these things appears to be the limiting reactant? The OH minus. So I'm going to subtract that from everything. And I'm going to be left with 0 for my hydroxide. I'm going to have .00050 moles of the acetic acid and the 0.00450 moles of the acetate ion. Now, at this point, because the hydroxide is completely used up, we have to understand that at some point the acetic acid undergoes some type of hydrolysis. And what I mean by that is that the acetic acid plus water, because it is aqueous, is going to form acetate ion and H plus. So now with that in mind, I can now write my Ka expression. So in this case, my Ka would be equal to the concentration of the acetate ion times concentration of H plus over the concentration of the acetic acid, like that. Now, I went to the handy-dandy Appendix B, or D rather, and identified that what my Ka value was. So I wrote that down here. Now, I have to calculate the concentration of the acetate ion after the in the new volume of the solution. So what that's going to look like is this. Where am I at? Oh, red. So I'm going to have the Do you follow that? Is that better?
Find molarity, right?
You have to find molarity. So if I just
Why did you rewrite the equation like that with adding water?
the reason why I rewrote the equation as I did was because I had to keep in mind the fact that all of the sodium hydroxide has been used up, and because acetic acid is aqueous by nature, it further hydrolyzes and produces H plus. So by doing that, I rewrote the equation so I could write the Ka expression for the weak acid in this problem. Maya? Okay. So once I calculated that all the way out, I calculated a value for my Ka, or I'm sorry, for my H plus to be 2.0 times 10 to the minus 6, which is equal to the concentration of H plus. So then I threw that up into the negative log of H plus. So the pH in this case would be equal to 5.70. So what's my majority species here? Yep. So it's going to be the CH3COO minus, and clearly the pH is going to be a little bit less than 7, but we are in our buffer system. Now example number 11, which we're going to do tomorrow, which will go a little bit more into this. So that's where we're at.